All right, recording this because a few of you are missing, so I want to make sure that you all get this. Welcome back from spring break. Before we left, we talked about solving trig equations. And so that's what we're going to pick up from today. And on Friday, we will have a quiz on that stuff. So this is what we went over before break started. And we did a bunch of these, and we solved all these between 0 and 2 pi. And now I want to kind of just touch on how we solve for all solutions. So the new assignment I gave is just kind of reviewing for the quiz Friday. It says to solve for all solutions. This one's just between 0 and 2 pi. So let's go back and look at number 1 for a second. So that's the sine of x equals root 3 over 2. So the sine of x equals root 3 over 2. And just a reminder of how we solved it for 0 to 2 pi. So we said, okay, we've got a unit circle, and the question is basically asking what values of x will make this true between 0 and 2 pi. And you say, okay, root 3 over 2 is right here, and it's right here. Remember, sine is our y value in the unit circle. So we get pi over 3, and then we get 2 pi over 3. There's nowhere else between 0 and 2 pi that makes this a true statement. And so we're done here. That would be our answer if we follow the directions and answer between 0 and 2 pi. And sometimes that's useful. We can talk about why we restrict it there and all that sort of thing. And that's what we're getting ready to do. What if I asked you for every single solution? So if we go back and look at graphing the sine of x, it looks something like, the sine of 0 is what? It's 0, because right here at 0, we're at 0. And then it goes through like this, doesn't it? Forever. And it goes in the negative direction like that, forever. And so we didn't really talk about it a whole lot when we graphed these because we just kind of graphed between 0 and 2 pi this year. But we could keep going forever. But somewhere in here there is root 3 over 2. And that's when we're at pi over 3, and then again at 2 pi over 3. We reach that spot where the y value equals root 3 over 2. But if you keep going this way, we intersect again here, and then again here, and here, and even in the negative direction, we get a y value of root 3 over 2, and it goes on forever. So there's an infinite amount of angles that will make this a true statement. Now that's looking at it on the graph of y equals sine of x. There's lots of times when y equals root 3 over 2 for an x value. But you could also look at the unit circle and find out those same values. Like right here at pi over 3, that's that angle right there drawn with that arrow. But if I were to add a circle to it, add a full 2 pi, it means we start right here at our initial ray and we go right there, and then we add a circle. So it's going to go around like that right there. Now remember, we talked about coterminal angles. Coterminal angles were found by taking a given angle, like pi over 3, and adding a circle to it. So that would be like adding 2 pi to it. So that is another angle. In fact, it's the angle, right here is pi over 3. If you add a full circle, it lands right there, whatever that is. That's the angle that makes that equal to root 3 over 2. We just added a full circle to it, or went a complete period from it. Then you could add 2 circles to it if you wanted to. So we could start right here, and it's going to get messy when I start drawing over top of this one. There's the first angle. Boom, there's adding 1 circle. And then boom, there's adding 2 circles. And you end up with a coterminal angle. That would be saying pi over 3 plus 4 pi n. Because 4 pi n is the same thing as 2 circles, right? 2 times 2 pi n. And so we could keep adding a bunch of circles. I didn't mean to put the n there. You don't want the n just yet. We could keep adding a bunch of circles to this and getting coterminal angles with pi over 3. Likewise, we could subtract circles from it. So you could say it's pi over 3 minus a circle, so minus 2 pi. Or pi over 3 minus, 6 circles. So 6 circles would be minus 12 pi. So you could add or subtract as many circles as you want, and that's how we're going to kind of phrase our solution. So this would be the answer if we were restricting it between 0 and 2 pi. But if I want every single coterminal angle with pi over 3, then I'm going to say, okay, you start with pi over 3, and we're going to add to it not just a single circle. That would say just add one circle to it. But we're going to add an infinite amount of circles in the positive and the negative direction. And the only way you can really write that is just to say 2 pi n, where n is a integer. So it can be 0, it can be positive, like your whole numbers. You can have 1, 2, 3, 4. You're basically just saying how many, it's a non-math way of saying it, but you can say how many circles are you adding here. And so if you added, like I said before, 6 circles, it'd be 2 pi times 6, which is 12 pi, except for we were subtracting it there. And that kind of brings up the point that we can let n be negative as well. So it can be -6, it can be -5, -1. And we get coterminal angles in the negative direction. If it's positive, we're going to be getting coterminal angles in the positive direction. And if it's 0, if n equals 0, then you get just that original angle that we solved for between 0 and 2 pi. You get pi over 3 there. And so saying just tacking on that 2 pi n will allow for all solutions that are coterminal with the pi over 3. Now what n cannot be is n cannot be a fraction that's between 0 and 1. Or just that leads you to a non-integer answer, I guess you could say. I'm trying to be technical here, but just keep in mind, like, the reason why I have to try to specifically say that, like, 6 over 3 is a fraction, but it reduces to a whole number, doesn't it? So you're okay with 6 over 3. But we don't want things like 1/2, we don't want 1/3, because you're not going a complete trip around the circle there. You're only going 1/3 of the way around the circle. And so that's why you don't want those fractions that don't reduce to a whole number or an integer. So same thing's got to be done with 2 pi over 3. 2 pi over 3 is right here, and we can add and subtract as many circles as we want from that. So I'm going to say plus 2 pi into that thing. So now we're adding and subtracting a bunch of circles to 2 pi over 3. We're adding and subtracting a bunch of circles to pi over 3, and this is my answer. So it's a little bit different. I know if you look at the solutions to this, yeah, it is from 0 to 2 pi, so it's just going to be these two. It's really not that much further of a step. You're just saying plus 2 pi n. I went through that 10-minute explanation because I want you to see why we do it. We're not just throwing the 2 pi n on there for nothing. So let's try a few examples. They'll go a little bit faster than that one. Let's try number 2 again. So number 2 is the cosine of x equals -1. And so first we'll just solve it for between 0 and 2 pi. So here's my unit circle, perfectly drawn. My camera battery went out, so you can't see my face now, but that's okay. The cosine of -1, remember cosine is our x value here. There's only one spot between 0 and 2 pi where it equals -1, and that's right here at pi. So my answer to this is x equals pi if the directions, pay attention to the directions, say between 0 and 2 pi. Only one spot, and that's at pi. If the directions were to say list all solutions, well then I'm going to add and subtract a bunch of circles to that. So add 2 pi into it. There's your answer. All right, let's try out another one here. Try out number 3, the tangent of x equals 0. And I'm going to go replace my battery while you check that over. All right, got the battery back in. So you can see my face. You can see when I frown and get confused and everything else. We got the tangent of x here equals 0. And remember, when we think about the unit circle and tangent, we're thinking about what is the slope of these lines on the angle there. So at 0 and then here again at pi, if you think about this line, its slope is 0 here and it's 0 here. So if we're trying to keep it between 0 and 2 pi, there are two spots where that slope is equal to 0. And that's going to be when x is equal to 0 and when x is equal to pi. We don't put 2 pi because notice if they're giving these instructions, they say do not include the 2 pi. So we can include 0, so that's why, technically we could call this 0 or coterminal with it is 2 pi. We're going to include the 0 if this is the instruction, saying keep it between 0 and 2 pi, but don't include 2 pi. And so from there we can add a bunch of circles if we want. If it's asking us for all solutions, we're going to say plus 2 pi n. Same thing here, plus 2 pi n. But the interesting thing about tangent is that tangent is always half a circle away because you're talking about the slope of a line. So even if you're talking, let's say, at pi over 3 right here, the slope there is root 3. So the tangent of pi over 3 is equal to root 3. But also down here at the tangent of, what is this, 4 pi over 3, the tangent of 4 pi over 3 also equals root 3. And so tangent, because its slope is always exactly half a circle away. And half a circle is pi. So, given this school year and how we've kind of had to sometimes accelerate our pacing and stuff like that, I'm not going to require you to, if you write it like this, I'm fine with that. But you could also, just as well, take one of these angles, doesn't matter which one. You can start with 0 there and just say plus pi n. Or you could say take pi and plus pi into that as well. You don't have to write down both of them. You can just write down one. And the reason why is we're adding not full circles here. We're adding half circles. So notice if you start here and add a half a circle, you land at pi. If you add half a circle again, you land at 2 pi. Add another half a circle, you land at 3 pi. Add another half, you land at 4 pi. And same thing right here. If you add half a circle, you land at an answer. Add half a circle, you land at an answer. And didn't trace a circle, that's fine. Add half a circle, you land there. And so with tangent, it's always half a circle away. With cosine and sine, not always the case there. If you look back at the first one we did here, with sine you had pi over 3 and 2 pi over 3. They're not half a circle away. So you have to write down both their answers and add full circles to them. Tangent, though, I'll take this. You can write those down and add full circles, or you can write down one of them and add half a circle with tangent. The only reason I would tell you that is because if you do see some of my work where I've written out the solutions, sometimes you might see it show pi in, and you might be wondering why did I just add half a circle? Why didn't I do this method? I'll take either one this year. I think that's fine if we look at it like that. All right, let's try out another one here. Let's see. Let's jump down and try to do a different one besides. We've done all 12 of these problems before, but I'm just kind of reviewing them, kind of get you back up to speed, and to kind of show you these full solution problems. So 4 sine squared of x is equal to 3. Let's solve this one for all solutions. This was number 11 on that, those practice problems we did before break. So as we go to solve this, just in case you forgot, we want to get that trig function by itself. So we're going to subtract 4, not subtract, divide by 4 on both sides. And while it looks like it's by itself, it's really saying sine times sine. We just want, kind of like if you had x squared, you're trying to get x by itself, you square root both sides. We're trying to get sine by itself, so we're going to square root both sides here. And so you get the sine of x is equal to the square root of 3/4. Now, if you recall our properties with radicals, if we're taking the square root of a fraction, you can rewrite this so it's square root of 3 over square root of 4. That equals the sine of x. And now we can take the square root of 4. We know it's 2. But don't forget, and maybe we should have written this in the beginning right here, that since we're introducing the radical, that we're going to put a plus or a minus in front of it. So really, this is plus or minus square root of 3 over 2. And if it helps you to think of it, you could say it can be the sine of x is equal to positive root 3 over 2, or the sine of x is equal to the negative root 3 over 2. That's the same thing as saying plus or minus. Keep in mind, that's the situation going on here. So we're going to go back, look at our unit circle. And we've got it, right here where it could be positive root 3 over 2. We actually did that at the beginning of this lesson today, where we had one like that at pi over 3 and at 2 pi over 3. But you could also have it at negative root 3 over 2. Negative root 3 over 2 is right here at 4 pi over 3. And then again right here at 5 pi over 3. So there's actually 4 possible answers between 0 and 2 pi. You could have x equals pi over 3, x equals 2 pi over 3, 4 pi over 3, and 5 pi over 3. That's if the directions say keep your answers between 0 and 2 pi like it did on the original problem set here. But we want all solutions now. So you could do what we did before and say, hey, and there's two different correct answers here I'll take. We could say add a bunch of circles to this one, add a bunch of circles to this one, add a bunch of circles to this one, and this one also. So let's go through and do that. Plus, 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 2 pi n. Remember, n can be positive numbers, it can be negative numbers, it can be 0, but it has to be a fraction, it can be reduced. So it can't be like 1/2. It has to be whole numbers there. It's not really whole numbers, it's integers, because you can have negatives in there. So that's acceptable, but it's redundant, all right? And the reason why it's redundant is because if, you don't even have to, I would say maybe not redundant's the right word here. It's just more than what we need here. It's a lot of writing here. When instead of adding full circles to pi over 3, you could just add half circles, because pi over 3 and 4 pi over 3 are half a circle away. So it's kind of like the tangent thing we did a second ago, where I noticed that, hey, these are directly half a circle away. So I'd also accept this as an answer, pi over 3 plus pi n, and 2 pi over 3 plus pi n. That's the same thing as this right here. And once again, the only reason why I'm telling you this is because you might see it in some of my answer keys in the work I already did where I put in a pi n. It should clue you in that, hey, some of the answers are only half a circle away from each other, so we're only adding half a circle or multiples of half a circle instead of multiples of full circles. Any questions on this stuff as we go through it? There's only a couple of you online today and one in class, but feel free to ask questions. All right, let's look at one more before we go today. Let's try to pick something that's interesting here. Let's do 2 times cotangent squared plus cosecant squared of x minus 2. We did this one, a couple weeks ago as number 8. But this time we're going to find all the solutions to it. this is one where we're going to need to use our Pythagorean identities, because when I start looking at this and say, okay, I got to factor out something, but they're not the same trig function. So if we use our Pythagorean identities, it will help us go through this a little bit faster. Now, sine squared plus cosine squared equals 1. That's where I always start. But none of these are sine or cosine, so I need to do something different here. So I try, okay, let's divide everything by sine squared. And this gives me 1 plus cotangent squared is equal to 1 over sine squared, which is cosecant squared. And so this tells me cosecant squared is equal to 1 plus cotangent squared. So where I see that cosecant squared, I'm going to substitute that out with 1 plus cotangent squared. And then everything else just comes down. So we've got a minus 2 and a 2 cotangent squared right here. And there's a plus sign in between this. And so from here I could kind of, combine things out. And so I've got 2 cotangent squareds right here and 1 cotangent squared right there. That combines to give me 3 cotangent squared. I have a positive 1 and a negative 2 here. Combining those gives me a negative 1. And now I'm in a place where I can say, okay, let's get cotangent by itself. So I'm going to add 1 to both sides. Divide by 3. And then square root it like I did on the other one before. Remember, when we square root this, we want to take the positive and the negative root. And so this becomes the square root of 1 over the square root of 3, which is 1 over root 3. You don't have to write all of this out. You can save some steps if you want. I'm just showing you how this is progressing. Now, if we rationalize this, this becomes plus or minus root 3. That's just by saying multiply the top and bottom by root 3. And you end up with, let's see here, root 3 over 3, actually. I almost left out that 3 there. And that equals cotangent of x. And then we're going to say, well, when does cotangent, actually, before I even go this far, I'm actually going to take it a step back to here, because I think it's easier to look at this. The cotangent of x equals 1 over root 3. And, we don't really have a lot memorized or tricks that we use for cotangent on the unit circle, but we do for tangent. And this is a super easy way that we can take something like this and make it a little more familiar. We say, cotangent over 1. If I flip the left side here and I flip the right side, what I get on the left side is tangent, and on the right side I get root 3. And that actually saves me from having to rationalize it too, right? So basically I'm asking, when is tangent equal to root 3? We've got 2 spots. You've got right here at pi over 3, and then you got right here at 4 pi over 3. Boy, these angles are coming up a bunch today, pi over 3 and 4 pi over 3. Strictly coincidence. It just so happens to be I'm picking up problems that land at those 2 spots. And so our answer to this question, if it's asking us between 0 and 2 pi, we write down both these angles, pi over 3 and 4 pi over 3. If it's asking us for all solutions, I'm going to say x is equal to pi over 3 plus a bunch of circles, 4 pi over 3 plus a bunch of circles, or you could just say pi over 3 plus a bunch of half circles. Since it's tangent, they're exactly half a circle away from each other. All right, only a few people in attendance today, but do you have any questions on what we went over? You good? All right. All right, well, there will be a quiz on this stuff on Friday that you'll take online. There is a review posted with some fresh problems, so if you're tired of these problems, you'll get some fresh ones, along with some solutions. So if you have any questions or need a little extra time, we can meet on Wednesday, or we can always meet after class. It doesn't really matter. Be happy to meet you and go over it. Thanks for showing up today, and I hope you have great afternoon.